What I've got here on the scope is a, well, let's call it passable approximation of a sine wave. And it all comes from the PWM output of an Arduino Nano filtered by a third order RC low pass filter. Yeah, there are 3 resistors here and 3 capacitors. In this video, I will try to explain how we get from this, a PWM output from a microcontroller, to an analog signal using an RC low-pass filter of nth order. And I will show you all the math required to do that. So we will have a look at the circuit diagram and the code of the Arduino. Yeah, there's a laptop here, and of course we will have detailed look at the oscilloscope. But most of the time we will stare at a piece of paper where I scribbled something. So strap in and enjoy. So the Nano on the breadboard was generating on pin 5 a 980 Hz PWM signal with an 8-bit resolution. It can do the same on pin 6. On pin 3, 9, 10 and 11 it generates only a 490 Hz PWM signal, also 8-bit resolution. That's basically something set by the Arduino base software. If you do a little bit of bit banging on the microcontroller used in the Nano, you can get up to a 8-bit PWM signal with 62.5 kHz or even a 16-bit PWM signal with, a meager 244 Hz. And these things might vary between different Arduinos and different microcontrollers. The important thing here is a PWM signal has a certain frequency and a certain resolution. Talking about PWM signals, these are basically just square waves where you can variate the duty cycle, okay? So this is the blue line, a 50% duty cycle square wave, and in PWM you can either shorten the duty cycle, following the green line here in between, or you can lengthen the duty cycle following the red line here. And there are 2 extremes. Duty cycle of 0 would be the signal is always off, and duty cycle 100% is the signal is always on. So in our case, again, we have a 980 Hz square wave with a variable duty cycle and 8-bit resolution. So we can vary the duty cycle in 256 steps, from 0 always off to 255 always on. If we have a zoomed in look at the oscilloscope, what's going on, we see here as we approach the top of the sine wave, our PWM signal is always on, giving us the maximum analog value. And before that, you see that the duty cycle is still quite high, but it's decreasing here to the left, as is the analog value. Accordingly, at the lowest point of our sine wave, our PWM signal is for a short time always off, and you see to the left and the right where our analog signal is rising again, the duty cycle is slowly increasing. The transformation of the PWM signal to an analog voltage is in our case achieved by a low-pass filter. That's not necessarily an RC low-pass filter. Any low-pass filter will do. And there are other techniques that achieve the same, and maybe we will talk about them towards the end of the video. But for now, let's stay with low-pass filters. The analog voltage we get after the low-pass filter follows ideally this formula. So our analog voltage is our supply voltage here. So yeah, the top of the square wave times the duty cycle in percent. So for example, for my blue wave here, 50% duty cycle, I should get half VCC. For the green with the short duty cycle, something below that. For the red with the longer duty cycle, something above that. And for 0%, I should get 0 volts. And for 100%, I should get VCC itself, ideally. In other words, a low-pass filter can give us the average voltage, not root mean square, the average voltage of our square wave here, and that's our analog signal. There are 3 parameters going into our design. First, the frequency of our PWM signal, of course. Second, what's the acceptable noise level at the output of our filter? In other words, how much of the square wave we still want to see at the output. Yeah, the ripple on our analog signal. And third, what's the analog bandwidth? Yeah, the bandwidth of our analog signal we need at the output. In this example, I will express the acceptable noise level in least significant bits. Our PWM signal has a resolution of 8 bits, so we have 2 to the power of 8, 256 steps. So 1 least significant bit is 1 divided by 2 to the power of 8, 0.00391 of full scale. My reasoning behind that is the following. If the green line would be our ideal analog output signal, yeah, I'm increasing it here in steps of 1 least significant bit, and I have a noise level of the amplitude of 1 least significant bit, I can still see the single steps without no problem. Note, that's my requirement. You might have others. You might say, okay, I want to see these steps a little bit more clearly. So let's go here for half a least significant bit. Or you can say, 2 least significant bits. Yeah, a little bit noise here. I don't mind. Or you can skip all that LSB calculations and directly go for that decimal number and say, okay, my acceptable noise level is, for example, 1%, that is 0.01, or 0.1%, 0.001. However you arrive at this decimal number here, you will have to convert it into decibels, because we're talking filters and so we're talking decibels. And that's the formula to convert such a fraction here of field values, that is volts and such, not power, field values, to decibels. Yeah, 20 times log 10 of our fraction here, and that gives us minus 48.2 decibels. Time to look at a nice picture for a change and not my ugly scribble. I haven't created that. That was created by a user named Inductive Load. It's in the public domain and from Wikipedia. I put a link down below in the description. It's showing idealized low-pass filter curves from first to fifth order low-pass filters. Remember, we are still talking low-pass filters in general, not RC filters specifically. These idealized filters are called Butterworth filters. And Butterworth is not a specific filter circuit. It's actually the mathematical description of these curves invented by a guy named Butterworth. On the x-axis, we have the relative frequency, one being the cutoff frequency or corner frequency of our filter, where it's down from 0 to minus 3 dBs, and then 10 times that frequency, 100 times that frequency in that direction, and a tenth of that frequency, and a hundredth of that frequency in that direction. And on the y-axis, we have our gain, which is negative, so our dampening really, from 0, that is signal going through 1 to 1, down to minus 100 decibels. Please remember, we're talking here output voltage divided by input voltage, so field values. That means every 20 decibels is another factor of 10, meaning a tenth, a hundredth, a thousandth, and so on of the input signal coming through. An ideal first order low pass filter goes down after the corner or cutoff frequency by 20 dBs per decade frequency, a second order by 40 dBs per decade frequency, third order 60 dBs per decade frequency, and so on. Generally speaking, an nth order filter goes down by n times 20 dB per decade frequency. With that out of the way, we can now choose the order of low pass filter we need for our application. And the first important line here on the y-axis is of course 0 dB, because that area here, usually up to the corner frequency, is the bandwidth our analog signal can have after the filter. I say usually because at the cutoff frequency we are already down minus 3 dBs. Logarithmic scale, that means about-ish 30%. That might not be acceptable, and you might want to design your filter so that your analog signal stays within an area where we are truly at the 0 line. The second important value on the y-axis is the attenuation we want for our PWM frequency. And I've drawn in here a line at minus 50 dB, which is near enough to the minus 48.2 dB, which we previously calculated. The line for the first order filter would intersect with our minus 50 dB line at about-ish 300 out here on the frequency scale, meaning our cutoff frequency for PWM signal of 980 Hz would be about 3 point something Hz. In addition, the curve of the first order filter deviates quite early from the 0 dB line at about 0.2 of the cutoff frequency. So if the minus 3 dBs are not acceptable for you here at the cutoff frequency, you are left with 0.2 of 3 Hz, so some tenth of a Hertz analog bandwidth for your output signal, and not good enough for me. So let's have a look at the second order filter. It joins our minus 50 dB attenuation line at about 20 of the frequency scale, meaning PWM frequency of 980 divided by 20 is about-ish 50 Hz here for the cutoff frequency. It also deviates from the 0 dB line a lot later at about 0.5. So 50 Hz times 0.5 makes 25 Hz bandwidth for our analog signal. Much better. So what I've done here already twice is I looked up the relative frequency where my filter curve meets the desired attenuation for the PWM frequency. and I divided the PWM frequency by that value to get my cutoff frequency relative 1 at -3 dBs. And if -3 dB attenuation within your analog bandwidth is fine for you, you stop here. Otherwise, you take the cutoff frequency and multiply it by the relative frequency where your filter deviates from the 0 dB curve. And this gives you really your analog signal bandwidth without any attenuation. 25 Hz analog bandwidth without any attenuation is still not good enough for me, and they say the third time is the charm, or maybe the third order filter is the charm. So have a look at that. It intersects our -50 dB curve at 7 relative frequency. 980 divided by 7 is 140. So 140 cutoff frequency, and it deviates from the 0 dB line at about 0.6. So 140 times 0.6 is aboutish 80 Hertz. That's good enough for me, so it will be a third order filter. If you're fine with the 3 dB attenuation at the end of your analog bandwidth, like most oscilloscope vendors are, there is a straightforward way to choose the order of filter you need for your application. You don't have to go through that whole trial and error process, which I admittedly dragged out a little bit. You take the PWM frequency and divide it by the analog bandwidth at -3 dB you desire, which is incidentally the cutoff frequency then, so here in our graph relative 1. And that gives you the relative frequency at which any filter you choose must have reached the desired attenuation for the PWM frequency. Let's say we want an analog bandwidth of 100 Hz at -3 dB, and we divide our PWM frequency of 980 Hz by that. That gives us a relative frequency of 9.8, so somewhere here on the frequency scale. And the first filter, to reach just before that the desired attenuation for our PWM frequency of -50 dB is again, the third order filter. Now that we've chosen the order of low-pass filter we need, we can actually calculate its required cutoff frequency. We don't have to rely on some graphic approximation here on the paper. We have math for that. And it was Mr. Butterworth who came up with all that math. This first formula here gives you the ratio between output and input voltage for an nth order low-pass filter, independence of the ratio of input frequency and its cutoff frequency. If you convert the ratio between output and input voltage into decibels, you get exactly the picture we've been staring at the whole time. On the y-axis in decibels, ratio input to output voltage, and on the x-axis, ratio input frequency to cutoff frequency 1. This formula can be rearranged into this form, and this gives you the required cutoff frequency for nth order low-pass filter to achieve a certain ratio between input and output voltage at a given frequency. That's exactly what we need. And if you want to know how to get from here to here, that's the way. I will not go into the details there. We've chosen a third order low-pass filter for our application, so N in that formula would be 3. Our PWM frequency is 960 Hz, so F is 960. And we already calculated the attenuation we want from that filter at 960 Hertz. It's 1 over 0.0391, and that goes here. And if you put all that in and type it into a calculator, you get a required cutoff frequency of 151 Hertz. Now that we know which order of low-pass filter we need and what its minus 3 dB cutoff frequency should be, we can finally start talking nth order RC low-pass filters. As mentioned before, RC filters are only one real-world implementation of those idealized Butterworth filters, or I should better say real-world approximations, as we will see. An nth order RC low-pass filter is really just n single RC low-pass filters in series. So this alone would be a first order RC low-pass filter, and if that dotted line wouldn't be here and we really had 2 resistors and 2 capacitors, that whole thing would be a second order RC low-pass filter, and so on. That's the formula to calculate the cutoff frequency of an nth order RC low-pass filter. And please note, I called that cutoff frequency FC prime because that's not exactly our minus 3 dB Butterworth filter cutoff frequency. Yeah, real-world approximation. More about that later. Anyway, with n equal 1, so just a first order RC low-pass filter, so simply RC, this gives us a cutoff frequency of 1 over 2 pi RC. Yeah, the first root of something being the something itself. The gain at the cutoff frequency is 1 over square root of 2 to the power of n. Again, with n equal 1, first order filter, that is just 1 over square root of 2 equals 0.707 equals our usual minus 3 dB. But for N2, second order RC low-pass filter, it's minus 6 dB. Third order, minus 9 dB. Or, yeah, more general, for nth order, it's minus n times 3 dB. That's where this little formula comes in. It gives us for nth order RC low-pass filter with a given cutoff frequency FC prime, our Butterworth minus 3 dB cutoff frequency. And again, for first order filter, n equals 1, this is just FC equals FC prime times, square root of 2 to the power of 1 minus 1, so square root of 1, so 1 equals FC square. So for first order filter, minus 3 dB at cutoff frequency, our Butterworth minus 3 dB cutoff frequency is the same like the one we calculated here. If we would draw a graph from the whole shebang like we had for the Butterworth filter, it would look like that. So frequency axis, gain axis, 0 dB line, minus 3 dB line, our first order, second order and third order filter curve, and only the first order RC low-pass filter would cut the minus 3 dB line at a relative frequency of 1. The higher the order of the RC low-pass filter, the more to the left it will cut the minus 3 dB line. Our idealized Butterworth filters all cut the minus 3 dB line at exactly the same point, relative frequency of 1, independent of their order. Fortunately, that little formula here can literally close the gap between real-world RC low-pass filters and the idealized Butterworth filters. It gives us for nth order RC filter and a given minus 3 dB cutoff frequency the required RC low-pass filter cutoff frequency FC prime. In graphical terms, it describes a shift of the higher order RC low-pass filter curves to the right, so they all go through that minus 3 dB point at a relative frequency of 1, like the Butterworth filters. By the way, this formula is basically that formula slightly rearranged. Yeah, just divide that by the whole square root term here and you get that. All that's left to do is to take our required minus 3 dB cutoff frequency of 151 Hz and our required order of our C filter, that's 3, into our formula, and we get an RC low-pass filter cutoff frequency FC prime of 296 Hz for a third order RC low-pass filter. And now it's finally time to calculate some resistor and capacitor values. In a real-world nth order RC filter, each RC element will usually have the same cutoff frequency, respectively the same time constant tau. So R times C1 is equal R times C2 is equal R times Cn, or simply R times C. If you recall the general formula for the cutoff frequency of an nth order RC low-pass filter, that's not a real necessity. In theory, for example, for a second order filter, you could design the first element to have a cutoff frequency of 10 Hz and the second element to have a cutoff frequency of 1000 Hz, and the filter as a whole would have a cutoff frequency of 100 Hz. There are applications for that, but not here. So if we assume that all our LC elements in our nth order filter have the value of tau, then we can write our general formula like that. Instead of writing here under the root R1 times C1 times R2 times C2, etc., we can simply write R times C to the power of n. And incidentally, the nth root of something, the power of n, is, the thing itself. So our general formula collapses to 1 over 2 PRC. And there the circle closes. And we are back at the cutoff frequency for a first order filter, which simplifies things enormously. Because that can simply be rearranged by multiplying with RC and dividing by FC prime into this. So tau equals RC equals 1 over 2 pi FC prime. And with the FC prime, we calculated for our third order RC low-pass filter of 296 Hz. That gives us a tau, or R times C, of 0.00538. Another important design rule for real-world nth order RC low-pass filter is to make each consecutive resistor in the chain smaller than the one before. The reason being, each RC element is an AC voltage divider. And what happens if you draw a current out of a voltage divider? Your voltage drops. So you want the current drawn out to be much smaller than the current going through the voltage divider. As a rule of thumb, you make each consecutive resistor 10 times bigger. So Ri is equal X boutish 10 times Ri minus 1. So the next resistor is 10 times bigger than the previous resistor. The bigger you can make X, the better. If you need to make it smaller, well, you have to live with the results. Anyway, keep in mind that your last RC element is also a voltage divider, and you still want to read that signal with something that has also a ideally 10 times bigger impedance than your last resistor. Another practical consideration is the minimum value of your first resistor. If you're driving that filter directly from a pin of your microcontroller, that pin can only provide so much current. And yeah, the on voltage of your PWM signal, that's usually the supply voltage of your microcontroller unit. So yeah, Ohm's law. R equals V divided by I. So let's finally choose some capacitor and resistor values for our filter. We already calculated tau, the time constant of each RC element, and tau equals R times C, so R equals tau over C. And I start with the capacitor values, C1, 1 microfarad, C2, 100 nanofarad, and C3, 10 nanofarads. So 10 times smaller in each stage. That in turn makes each resistor in each stage 10 times larger. And the first resistor, R1, that's our tau 0.000538 over 1 microfarad, that gives us 538 ohms. So R2 5.38 kilo ohms and R3 53.8 kilo ohms. Yeah, these values do not exist, or they are very expensive to come by. So I choose the nearest values from the E24 series, and that would be 560 ohms, 5.6 kilo ohms, and 56 kilo ohms. And now let's have a look at the schematic. And that's all what's on the breadboard today. The third order RC low pass filter we just designed, connected to the pin 5 of my Nano. And I also connected some oscilloscope probes, so channel 1 is showing the raw PWM signal, we already had a look at that. Channel 4, the final output of our RC low pass, we also saw that, but I also connected channel 2 and channel 3 after the first RC element and the second RC element. So I guess it's time to return to the oscilloscope and have a look at some pretty pictures. And a pretty picture it is. So yellow is our PWM signal. The broad blue strokes here, that's after our first RC element. And you may be able to spot these not as broad reddish strokes. That's our channel 3 after the second RC element. And the output of our filter is that thin green line here. Okay, let's zoom in a little bit. At that time scale, you can see how the PWM signal is changing the duty cycle until here. Yeah, at the very top of the sine wave, it's always on for just a few cycles. After our first RC element, yeah, the bluish line, it's already a little bit sine wavy, but also still contains a whole lot of the PWM frequency. Yeah. Second RC element output, much better. Maybe some people might be okay with that, but yeah, still some PWM frequency in it. And then green, our final output. Of course, it still contains some ripple. We designed it that way. But very sine wavy. And of course we will measure the ripple to check if our design really met our requirement in regards to that 1 LSB maximum ripple in there. But let's zoom in a little bit more. Now you can see, or at least guess, the phase shift that is generated by all those RC elements. I mean, we are operating then at about-ish 7 times of their cutoff frequency, so the phase shift of each RC element is approaching 90 degrees. So after our first stage here, you see the maximum of the first stage is a wee bit delayed compared to the maximum of our PWM signal. The reddish line, you can clearly see that the maximum comes a few cycles after the maximum of our PWM signal. And the green line, it has a maximum clearly here, where the PWM signal is already ramping down again. I'm zoomed in here on the 180-degree point of our sine wave, where the signal changes the fastest, and I put some cursors here to measure the noise that is left on our output signal. And please note our maximum amplitude is 4.4 volts about-ish. So if we have a closer look, I'm measuring here just that ripple that is left in the signal, and it's about 70 millivolts. Well, 4.4 volts divided by 70 millivolts is 0.016. Our design goal was 0.00391. So we are about a factor 4 of our design goal. But let's try to get a better measurement. Give me some time. Nope. Zooming in even worsened the situation, getting my accuracy. I'm measuring now 84 millivolts ripple here left, and we were aiming for about-ish 17 millivolts. So what's happening here? Why is the real filter so much worse than our theoretical filter? The culprits are, of course, your real-world resistors and capacitors. I mean, these resistors also have a little inductivity, and your capacitors, especially, the electrolytic here, the 1 microfarad one, it has probably quite a high series resistance. Maybe we can do something about that. Give me a sec. I replaced the electrolytic capacitor by a ceramic one. That should have a much lower equivalent series resistance. Let's see what the scope says. And indeed, that little change shaved off about 6 millivolts on our ripple. So keep in mind, real-world capacitors and real-world resistors don't behave like ideal ones, so you have some discrepancies to the perfect math, and they come with tolerances. My resistors have plus minus 5% and my run-of-the-mill ceramics plus minus 10%. And the electrolytic even had plus minus 20% tolerance. You have to make accommodations for that too. And the real world strikes on another front too. See, the peak voltage of my output is 4.45 volts. And it does not go down to quite 0 volts. It stays at a few dozen millivolts. But that's not all. I just swapped the USB power supply of my Arduino, that was the old one, with another one. And you see the output voltage is now 4.57 volts. So it changed. And basically, if you want really precision on your amplitude, this whole approach is not for you, because the 5-volt rail, which should be on top here, is not really stabilized. It has absolutely no precision. If you are lucky, the rail will give you plus minus 5%, minus the real world dampening you're experiencing here. Yeah, so absolutely no precision on the amplitude. Okay, enough of that analog stuff. Let's have a look at the code. So I have a constant here, PWM pin, which is a 5. I have a constant PWM frequency, which is 980 Hertz. Yeah, I'm back to 980 Hertz. And my sine wave frequency I want to generate is 10. So the first interesting thing is I'm calculating here the number of steps, of digital steps in which I want to approximate my sine wave. And that's simply the PWM frequency divided by the sine frequency. I will talk a little bit on paper about that in a minute, but yeah, that's the absolute theoretical maximum that makes any sense. It makes absolutely no sense to have a higher resolution. Anyway, I also calculate the microseconds per step. Don't want to change my code here, which is simply, 1 million, it's microseconds, divided by the sine frequency and the number of steps. Okay. Then I have here a byte array, with my sine values for each step. And these sine values are already scaled from 0 to 255 as I need them for the analog write command later on. In my setup, I simply go through a loop in which I fill that array with the appropriate sine values. And I of course say my PWM pin is output, and for some reason, I don't know why, I set it to 127, so 50% duty cycle for a start. Anyway, the loop itself is quite simple. So forever, I go through the steps in which I have digitized my sine wave. And in each loop, I first calculate when I have to perform the next step. So the current time in microseconds plus the time a step should take in microseconds. Then I write my PWM value from my array for the appropriate step to the pin. And then I wait until the time I calculated has arrived, and then next step, and so on. And that's all the code there is. Let's talk real quick about that PWM frequency, sine frequency, and number of steps stuff. So the PWM frequency is kind of like the sampling frequency of a digital oscilloscope or a digital function generator. In each cycle of that square wave, you can output exactly one value. I mean, kind of self-evident. You can only modify the duty cycle here for one of the cycles once. So, the duty cycle is your value. So if you have an analog frequency or any analog signal, a periodic signal, you want to output on the PWM pin, it doesn't make sense to have any more samples than the PWM frequency divided by the frequency of your analog signal. So for example, if I would take a sine frequency of 100 Hertz, I'd had 9.8 samples left to somehow I don't know if that will be 9.8 samples, probably not. These are a little bit more, but yeah, you see what I'm saying. This is really your sampling rate, and building bigger lookup tables for your sine or other function you output makes absolutely no sense. And of course, this is also a digital limitation for the bandwidth of the analog signals you can output. In the intro, I mentioned I might talk about better ways to do that. Yeah, getting analog signal from a PWM signal generated by your MCU. And yeah, our main problems we have with this passive RC filter we built is, our amplitude, it's varying with the VCC of the MCU, and we still have some noise left. And as long as you use filter, you always have some noise left. But maybe we can solve the amplitude problem. All we have to do is to take a real voltage reference, which gives us a precise and stable voltage, and electronic switch, aka MOSFETs, that is driven by our PWM signal. And then we add some active filters, that can account for the dampening of your RC or LC elements. And we get still with some noise, a sine wave, but with a stable amplitude. Or we could feed our stabilized PWM signal into a resettable integrator, which output would be proportional exactly to the duty cycle of our PWM signal. And after each PWM cycle, we can sample and hold that signal and output it. The whole thing would have to have some control unit, resetting the integrator and telling the sample and hold circuit to when to sample and when to hold, and we could control that by the edge of the PWM signal, and we would get a very nice sine wave out of it. If you would zoom in here, you just have that stair here without any ripple on it. Very nice. By the way, the whole shebang, if you include the PWM generation itself, is one possible architecture for a digital analog converter. And you can buy those. And they talk directly, digitally with your MCU and output a very nice, very precise, very low noise analog signal. But that's something for an upcoming video or two. And with that and our still quite respectable sine wave in the background, I say bye.